And we worked on optical properties of dye crystals at NYU with Professor Bart Carr. And we worked on different types of crystals that we grew. And these are just different chemicals that we use. Like this is KAP, and these are different KDP. So, what is a crystal? Crystal is a solid formed by a repeated pattern of a unit cell. And what's a unit cell? What it is that there are many types of unit cells. There are primitive type, which is a cube, and it has atoms on each corners. Then, what it does is that it takes that cube and it repeats many times. So when you see a crystal, inside you see these type of patterns formed. But these are just the simple ones. There are many types, like B-centered becomes more complicated because then you see atoms on these sides on the different surfaces, and they start to become more complicated. But these are just examples. We're dealing with something much more complex than this. And 2D, it looks pretty geometrical, like you see the lines, but in 3D it's much harder, so you can't really detect the lines. And what we use to grow crystals are, we use different chemicals. We use ammonium perchlorate, we use KDP, which is potassium dihydrogen phosphate. We use KAP, which is potassium acid phosphorate, copper sulfate, and urea oxalate. We use different dyes also, like xylitol orange, Bismarck brown, methylene blue, and they look more like these type of dyes. So then we use hot plate, distilled and deionized water, crystal dishes, stirrers, temperature and control valve, and we use computer programs to draw the molecule structure, and we use the MATLAB, Avogadro, and Gaussian.
How to grow a crystal. Most likely we use 17 grams of EDP and 4 milligrams of dye. After that, we place the KDP with DI water. We heat up till it dissolves, and after that we add the 4 milligrams of dye. Then we place the solution in the crystal dishes, and we wait till at least 1 hour to see the final crystal.
I'm gonna go for this experiment with it. We grew these crystals, as you see here. Yes, we did grow them that color like that. That's amaranth, silent orange, methylene blue, Victoria blue, and Chicago sky blue. That's me caught in a crystal. What we used was a piece of rope, it's a string, cotton string with water, just back and forth at the same time. And what water does is it dilutes the KDP, and once we cut the part that we need to see the dye creation, then we just polish it down, and that's amaranth. That's the molecule how the dye looks. Investigation with polarized light. This is dichroism. What dichroism means is dye, which means two, and chroism means color. So it's two colors that we need to find out. Linear polarized light is electrified through waves. They go back up and down, back and forth. And what we do with that is that we place a crystal in a 90-degree form. And when with a linearly polarized light, what it does is that it shows a different color. And as soon as we turn 90 degrees to the left of the crystal, we see another color. Like that's we see the orientation of the dye, which it has like a stronger concentration of that and a weaker concentration of that. With circularly polarized light, there are electric fields going in a helix. Helix means spiral. We see the different absorption of left and right light. And we see the symmetry of the dye, which means like if we put the circularly polarized light through a crystal, what we're gonna see is some different colors of light, same as with linearly polarized light. That tells us which side the dye prefer the most. These are results we use with a spectrum. And we see this chart, which means that 600 plus is red, and 600 and below is blue. So this is methylene blue dye in a crystal of KDP. So we see that the absorption is on 600, which means it absorbed the red, so that means that the crystal is blue. So this is what we want to find out when we grow crystals. And that is the main dark line means the strongest absorption, and the dotted line means the weakest absorption.
Our main goal is to measure the circular dicrostate or a chiral dye molecule or internal crystal. And a chiral molecule is that it could be superimposed on their mirror image. As we can see in the image, the real molecule is imposed in its mirror image. In the other image, we can see the red bubbles indicate the right circular polarizer, and the blue bubbles indicate the left. And through this, we're trying to find out how the dye is oriented in the crystal.
And this is our bibliography, and our acknowledgements go to Professor Barnard, Dr. Ruben Paradise,
John for the info, Veronica Murphy, Dr. Sack, Dr. Ross, staff member,
and
this picture right here is just not a picture. It's not just a simple picture. That's actually in Russia. Recently, it was found out that that crystal is actually a twistable crystal. It means that when it grows, it twisted itself. And while it finishes growing, it untwists again. So that's how actually the crystal looks with a really close look through a microscope. So the different colors means the different twist. Like how much does it twist? Like let's say you see black and then it goes back to black. So black starts, and when it hits on pink, the pink is when it starts twisting. So that's how the actual crystal looks, and that's a new discovery in Russia, which is awesome. So any questions, guys? So I'm going to mention the circular dichroism. So on an 8 chiral dye, we found out that like if you put your hand over further that means that's chiral, right? So if you put your hand like that, it's 8 chiral. It means that if you have a cylinder, like if you twist it, it'll look the same. But in here, we're using dyes and crystals, like when you turn them around, it'll look different. So what we did was we used MATLAB and Avogadro and Gaussian so we can find that. And what we did is that with a dye, we polished the crystal all the way down. When we take this special microscope to look through with a polarized light and circularly polarized light, it gives you the information about the dichroism of the crystal dye. So when we twist the crystal in a certain 90 degrees angle, which is going to take us to the red bubbles that is looking to the center of the diagram, because it's a 3D molecule. So we look through the red one, we send right polarized light, which indicates, we send left and right polarized, circularly polarized light, and once we send there, we know that if we receive only left, it's because the crystal is perfectly dyed. itself. So if we send the circular polarized light through the right side, and we receive right polarized light, it means that the crystal did not die at all. Any other questions? Yeah.
So you use these diagrams to find how the dye is oriented in the crystal.
Yes.
Why do you do that? What do you use that information for?
Okay. Yeah, this is some. He said that. Why do we use this for information kind of bad? What we're trying to get here is like here we are the only ones like different. It's kind of hard to explain this, but what we're trying to do specifically is trying to get information from crystals dyed, which nobody here in actually United States take care of. Like this is a new concept that almost nobody takes care of. That we're trying to bring it forward, we're trying to actually find information on dyed crystals. Any other questions? Thank you.
Of how light is being absorbed. So we send these crystals to the, what do you call it? Like when you use it, I don't know what to call it. like send it in the, what do you call it? No, send it in the air. Space, but yeah, send it to space. And there they use it for certain reasons. I don't know why.
I can answer that question. We use these crystals because there is a major experiment going on in the United States with we're growing these huge, gigantic crystals, and they need to be perfectly formed. So for us to do this, we try to get the more accurate information about crystals. If we do that, we make history actually. So this is a really interesting experiments we're doing, and what this means is that if we actually get that, we can send that information to where these crystals have been grown, which is in Washington State, and what we can get is for that, just send the information.
Yeah, you can even make medicine.
Wow.
Because when the shape of the
Medicine.
yeah, you can make, because this is also used in Alzheimer's disease. They found crystals in Alzheimer's disease, but that's not what we're dealing with. But they can also make medicine things,
Right.
slicing the brain and different processes.